Okay, in this video I'm going to try to describe the relationship between how we do computations with discrete random variables and how we do computations with continuous random variables. And my hope is that you'll see the connections between them and you won't have to think about continuous random variables as this completely new topic that's separated from the discrete random variables, but instead that you'll just see the slight difference and be able to work off of the similarities. So this is going to be titled integrals instead of sums, because that's really what we're doing. That's all we're doing with continuous random variables. So let's suppose we have a random variable x and we want to compute the probability that x is between 2 and 20. Let's see, so the probability that 2 is less than or equal to capital X less than or equal to 20. If your random variable is discrete, then what would you do? Well, you would just add. You would add up from k equals 2 to 20 the probability that x equals k. Now, what would you do if the random variable was continuous? Well, it's very similar, but this time we're integrating an infinite number of infinitesimally small values. That's what it means to have a definite integral. So we have the integral from 2 to infinity of f sub x of x dx. I should put that dx there. And to clean it up a little bit, I'm going to make this 2 size 24 and this 20 of size 24. So you see that these really are pretty similar. Instead of having a discrete sum, we have an integral for the continuous case. Notice that the sigma is replaced by the integral sign, so the sigma is replaced by the integral sign. And then the probability that x equals k, is replaced by the PDF, the f sub x of x. Okay, so that was the first thing I wanted to talk about. Next thing I want to talk about is expectation. If we're in the discrete situation, and let me actually pull this down a little bit more so we can get it separated. If we're in the discrete situation, then remember that the expectation is defined to be the sum, and we sum over all possible values. So long as our random variable only takes integer values, that'll be from negative infinity to infinity, of k times the probability that x is equal to k. So we multiply the values by their probabilities and then add them up. What about the continuous case? Well, we haven't talked about this yet, but it's going to be very similar. And that's why I wanted to introduce it in this video, because it really is not that much of a new thing. To calculate the expectation for a continuous random variable, we take the values, in this case x, times the probability. But the probability for a continuous random variable is encoded in this PDF f sub x. Okay, so that's how you compute the expectation for a continuous random variable. Notice that again, we're leaving our limits the same, limits of summation up here, limits of integration down here. And we just multiply the value times its probability, but for the continuous case, the probability is replaced by the PDF times dx. Okay, and finally we need to work with standard deviation and variance. So if we have variance, and by the way, the expectation as before, as with continuous random variables, that's denoted expectation of x, or you can call it mu for the Greek letter mu. Let me see if I can find it. Right there it is. Okay, and the variance we can denote by sigma squared. Whoops, I need to be on math mode to do that. And it's also sometimes denoted as var of x, using capital var for variance. Or excuse me, VAR for variance. Well, in the discrete case, this was the expectation. Let me turn to math mode. The expectation of, let's put this in brackets, x minus the mean, mu, squared. So it's the expected squared difference of the random variable from the mean. And for the discrete case, that meant that we sum from negative infinity to infinity. So from k equals negative infinity. I don't know why that sometimes gives it to me small and sometimes large. And then I don't know why when I talk I can't seem to operate the keyboard very well. There we go. Let's change that to size 24. And then here we're going to insert an infinity. I think as long as I don't delete that letter, it's okay. Okay, so I take k and I subtract the mean. I could put e of x, or I'm going to put mu here for the mean because it's just a little bit shorter to write, and I'll make this bigger in a second. I square that, and then I multiply by the probability that x is equal to k, and I add all those up. And again, this is the case so long as your random variable only takes on integer values. If you had a random variable that's a discrete random variable and it takes on, for example, fractional values, then you would replace this summation from negative infinity to infinity with summation of k in the set of possible values. Give it a name. We've been calling it s in this class. Okay, so we already know that. We already know that that's how you compute the variance for a discrete random variable. You take the expectation of x minus the mean squared. For a continuous random variable, it's, well, the same. So if we have a continuous random variable x, then to compute the variance, it's the exact same thing. We still have the expectation of the squared deviation of the mean. But since we are dealing with a continuous random variable, this is going to look a little bit different. And this is looking really funny compared to what's up here. I wonder why it looks different. Okay, that's in italics. Yeah, I don't know why it looks different. Anyway, the summation changes to an integral. Okay, so we have the integral from negative infinity to infinity of x minus mu squared, just like up there we had k minus mu squared, times the PDF, f sub x of x dx. And let's change all this to size 24s. I hope to eventually get better at this. Once I do get my pen pad, I'm going to ask you all, and I probably will have asked you already by the time you watch this video, if you prefer me typing or if you prefer me writing. So if I do end up working with Maple more, I'm sure I'll get better at working with the font size here and having it be what I want to be. Okay, so that's it. That's how we're going to compute the variance for a continuous random variable.